Okay, so the question we are going to answer today is describe the role of surface free energy in phase transformation nucleation. So when we talk about phase transformations or the nucleation of a new phase, our minds want to go to, liquid to solid. So like water freezing is a nucleation of a new phase or a phase transformation. But in material science, and specifically metallurgy, oftentimes we have solid to solid phase transformations, where we have one solid phase or solid crystal structure, and then we do something to it to precipitate out or to grow a new phase from it. So maybe we would heat our material and heat it in such a way that we have ions diffuse to the grain boundaries and form a new phase. Or maybe we introduce another element, change the composition, that forms a new phase. And so when we think about solids, like solids compared to liquids will move, right? Liquids they don't have a strong interaction between the molecules, but solids, when you form a new phase, that applies stress on its surrounding environment of some sort, and that can have, and in that way, we have like a more complex system. And so when we have, and so then why do atoms want to go to this new phase? What is it about this new phase that makes it worthwhile? And what makes it worthwhile is thermodynamics. Basically, what we're saying is that in this new phase that we're forming, there's a promise of a lower energy state. There's a promise that atoms in this lower energy state are thermodynamically more fireable because they have a lower average energy. And that could be due to many reasons, but it's just this idea that this new state, you have a lower energy. And that's all atoms really respond to. So okay. So actually, okay. So when the new phase is really small, right? When the new phase is just starting out, it's really small. Most of the atoms of this new phase are in the interface, right? They're on the edge of this new phase. So the interface between the new phase and the existing matrix, right? So in that case, atoms have like, all the atoms are by the surface, and the surface is the interface between the two phases, and that's a high energy state, right? That's because you're not in one crystal, you're not fully in another crystal, you're in the interface between two, and that's a high energy state. So that actually is bad. That's actually not so energetically favorable. But as the new phase begins to grow in size, then the atoms in the middle of the secondary phase, they become happy because they're at a lower energy phase. They had the promise fulfilled of having the of the secondary phase with a lower energy. So what ends up happening is there's an interplay between between surface tension at the interface and the volume expression of having the lower thermodynamics in the volume. So that can be described as this. Here we have the alpha matrix phase and the new beta phase, and along this along the interface or the surface area, that's a region of high energy, but inside the bulk of the beta phase, that's the area of low energy. And if we think about what volume is and what area is, right? So area is like a length times a length, right? So it's centimeters squared. But volume is centimeters cubed, right? So you would think, okay, eventually, if this is a sphere and we're graphing this as a function of radius or the size of the new phase, right? One is growing by a factor of an order of 2, and one is growing by an order of 3. So eventually, if we get a secondary phase large enough, the thermodynamic promise of going to a lower energy state will outweigh this surface tension or this interfacial energy, and that's exactly what we see happen. So let's see what happens. So here we have the Gibbs free energy of the system, right? And it has, if you're familiar with Gibbs free energy, if it is negative, it's spontaneous, right? So if the Gibbs free energy of a system is negative, that means that system, that reaction or event will proceed. And if it's positive, it means that that reaction or event won't proceed. And here we are describing Gibbs free energy as a function of the volume and the surface area components, right? So the volume, hi. So as we said before, the volume component, we'll describe that as so we have 4 plus pi r cubed, right? So that is just the volume of a sphere times this Gibbs component. And if we wanted to, we could derive the Gibbs free energy of a system, all of that stuff. But like, why? Why would we? That's a lot of time. We don't want to do it. So basically, we're just going to say that this is some constant, right? And if we graph that, it will look something like this. It takes a little while to get going, but once it gets going, it really decreases a lot, right? Likewise, we have this surface area term. And the surface area term we're going to describe as, you know, the surface area of a sphere. And we're going to say that that is 4 pi r squared times this gamma. And this gamma is just a surface area coefficient between the two phases. So if you have a large, say for example, you have a large crystallographic difference between the two phases, you're going from like a BCC phase to a FCC phase, for example, this would be higher. Maybe there's a lot of disorientation or disalignment. This could be higher or lower to adjust for that, but it's also, we're going to view it as constant. So if we graph the surface area component, it'll look something like this. And now, so, but we said that the total Gibbs free energy of the system, the total Gibbs free energy of the system is the sum of those two. So if we sum the two, it'll look like this. Well, this, wait, so this is right. And so what we have here is the Gibbs free energy as a function of precipitate size, or the function of the size of the new grain. And at really low radiuses, we see that the surface area tension is higher than the free volume thermodynamic component. So we have a positive Gibbs free energy, right? But then eventually it comes to a point here where the particle is big enough that now more atoms feel the favorable effects of being in the new phase than the surface area effects, and the Gibbs free energy becomes negative very, very rapidly. And in this way, this graph serves as a critical nucleation radius, right? So this point right here, if a precipitate is smaller than this radius, it's unstable and it won't last. But if it's larger than this radius, then it will be stable and continue to grow. And so what's happening, you know, atoms in matrix in real life, you know, they're very dynamic systems, and atoms are constantly going all over the place and vibrating and doing all these things. And they're always spontaneously, you know, they can be spontaneously forming bonds and breaking bonds, especially in metals where, like, you know, there's a lot of electrons going everywhere. But oftentimes these spontaneous events that occur, you know, are in this range. So they form very briefly and then they are immediately, you know, destroyed just because they're not any more stable than the parent phase. And it's not until we have a particle of a set size that we precipitate a new phase. And so it becomes pretty yeah, so it becomes pretty a useful tool because we can use material science or trends in material science to tune the surface area parameter and the volumetric parameter. And we can engineer material that maybe won't nucleate as easily or material that will nucleate as easily. And in this way, we can begin to really control the crystal structure of our system. So for those who are interested in this, this is section 10.3 in the book. Yeah, so, and this will become important because the next thing we're going to talk about and discuss is steel, and specifically the different, you know, how we get different phases of steel. So I'm going to now attempt to draw the steel phase diagram. I had it memorized. Phase diagrams. Okay. So this is a phase diagram, and phase diagrams that we will discuss always show temperature on the y-axis and chemical composition on the x-axis. And in this case, we're doing chemical composition of carbon in iron. But in this case, we aren't going to 100% carbon. We're only going to 6.7% carbon. That's the upper limit of carbon in steel. If we have any more carbon in steel, we form this thing called cementite. We also know it as cast iron, right? Like, so above this percentage, it's not very interesting. So we're like, okay, we're done with that. Like, cast iron's cool for cooking, but you know, not much else. Okay.
I don't understand.
Go away. So over here, first thing I drew was the alpha phase, also known as ferrite. So that's the alpha phase. And here we have cementite on this side. So everything between the alpha and the cementite phase is a mix of the two. So in this region below here, we have alpha phase, the cementite phase, which is Fe3C, and then alpha plus Fe3C. Okay. The other major phase we have is here. Looks something like this. The gamma phase here, and the gamma phase is also known as austenite. So now we have two regions here. This is the alpha plus gamma phase in this region, and here we have gamma plus cementite. Okay, and then lastly, as we go up, so if we heat everything up really hot, we know we just get a liquid, right? If we heat everything up super hot, we'll melt it all, we get a liquid. And then in between, we have the gamma plus liquid phase. And then here we have the liquid plus cementite phase. And then all the way up top in this corner, we have the delta phase of steel, but we just kind of don't really, we're not too worried about that one. So it exists, it's up here, that's why we drew it, but we're not gonna like really stress out too much about it. So what we will do when we discuss steel, we're gonna discuss hyper and hypoeutectic transformations of steel. So the eutectic point is a point where there's a depression in the the intermediate phases here. So this right here is the eutectic point. It's a point where we go directly from one phase to another, right? So we have a direct phase transition, right? So we go directly to this austenitic phase, to this alpha plus cementite phase. But here we have a transition period between austenite and ferrite where we go austenite, austenite plus ferrite, and then just ferrite. So the eutectic point is described as this depression between which you go directly from phase A to phase B, and you don't have these intermediate phases here. It's kind of tricky though, because in this case we're going from one phase to two phases, but it's still an austenitic transformation. There's a second eutectic point on this diagram right here, where we go from a liquid phase to a solid phase without having any intermediate liquid plus solid phase. And that's a little bit easier to wrap your head around at this point here. But in general, when we talk about steel, we're discussing this eutectic point, the austenitic eutectic point. So hypereutectic means anything to the right of it, because we're at higher concentrations of carbon, and hypoeutectic is anything to the left of it with lower concentrations of carbon. Cool. Okay, so next week we will discuss the various phase transitions that can occur as we traverse the phase diagram in a hypoeutectic transformation, a eutectic transformation, and a hypereutectic transformation. So thank you for your feedback today. I will definitely be talking with Clive, or Dr. Clayton rather, about the exams moving forward and what is best for everyone. I will let you all know about what we come to, and I hope everyone has a good weekend and tries to stay sane. So, okay, thank you. And I will talk to everyone soon. All right, bye-bye.